What if the universe never began? Not in the sense that it has always looked the way it does now, but in the deeper sense that there may have been no first moment at all, no single instant when everything switched on from nothing. For most of the last century, science has told a different story. The universe started in a hot, dense state, expanded, cooled, and produced the galaxies, stars, and planets we see today. That account is supported by some of the most precise measurements ever made. Yet at its very foundation sits a problem that refuses to go away. Trace the expansion backward far enough, and the equations stop describing a universe at all. They collapse into a point of infinite density where space, time, temperature, and curvature all lose meaning. Physicists call this the singularity, and it marks not an explanation, but the place where explanation ends. This is where a different possibility enters. What if that apparent beginning was not a beginning, but a transition? What if our universe is one phase in a far longer process, a cycle that has repeated before and may repeat again? These ideas are not mystical. They emerge from serious attempts to fix the gaps in the standard model using general relativity, quantum theory, and the strange mathematics of higher dimensions. In the chapters ahead, we will examine the evidence for cosmic origins, the cracks in that evidence, and the growing family of theories suggesting the cosmos may have no starting point at all. We begin with the oldest question of all. The question of whether the universe had a beginning is older than physics, older than written language, perhaps as old as human thought itself. Long before anyone could measure the distance to a star or calculate the age of a rock, people looked at the night sky and wondered how it all came to be. Many ancient cultures imagined a moment of creation, a first event from which everything else followed. Others imagined the opposite, a cosmos that had always existed, with no first day and no final one. These were not scientific positions in any modern sense. They were intuitions, attempts to make sense of existence using the tools available at the time. What is remarkable is that the same two possibilities still frame the deepest debates in cosmology today. Either the universe began, or it did not. Everything else is detail. For most of human history, this question seemed permanently beyond reach. There was no obvious way to investigate the origin of everything. You cannot run an experiment on the birth of the cosmos. You cannot travel back to witness it. The subject belonged to philosophy and religion, not to the careful business of measurement and prediction. That began to change in the early part of the 20th century, when a series of discoveries transformed cosmology from speculation into a quantitative science. For the first time, the question of cosmic origins became something that could be approached with equations and telescopes, rather than pure reasoning. And the first thing scientists discovered was that the universe is not static. It is not a fixed stage on which events unfold. It is changing, growing, and that single fact carries enormous implications. To understand why this matters, consider what most thinkers assumed before the 20th century. The prevailing view, held even by many leading physicists, was that the universe as a whole was essentially unchanging on large scales. Individual stars might form and die, but the overall structure of the cosmos was thought to be stable and eternal. This seemed reasonable. When you look at the sky over a human lifetime, nothing appears to move. The constellations your grandparents saw are the constellations you see. The idea of a universe in motion, expanding outward in every direction, would have struck most people as absurd. Yet that is precisely what the evidence began to suggest. The key insight came from studying the light of distant galaxies. When astronomers analyzed that light carefully, splitting it into its component colors the way a prism splits sunlight, they found something unexpected. The light from galaxies was shifted toward the red end of the spectrum. This shift, now called redshift, has a natural interpretation. When a source of light moves away from an observer, its light waves are stretched, lowering their frequency and shifting their color toward red. The faster the source recedes, the greater the shift. What astronomers found was that almost every galaxy showed this redshift, and more strikingly, that the more distant a galaxy was, the faster it appeared to be moving away. This relationship between distance and recession speed became one of the foundational observations of modern cosmology. Think carefully about what this implies. If nearly every galaxy is moving away from us, and the most distant ones are moving away fastest, it might at first seem that we occupy some special central position, with everything fleeing from our location. But that interpretation is mistaken. The correct picture is far stranger and more elegant. Space itself is expanding. The galaxies are not flying through space away from a central point. Rather, the space between galaxies is stretching, carrying them apart from one another. An observer in any galaxy, anywhere in the universe, would see the same thing we see: all the other galaxies receding, the distant ones faster than the near ones. There is no center. There is no edge from which the expansion proceeds. Every point is moving away from every other point, like marks on the surface of an inflating balloon, each spot growing more distant from all the others as the balloon swells. This analogy is worth dwelling on, because it captures something genuinely difficult to visualize. Imagine the two-dimensional surface of a balloon covered in small dots. As you inflate the balloon, every dot moves away from every other dot. No single dot is the center of the expansion, because the expansion is happening across the entire surface. A creature confined to that surface, unable to perceive the third dimension into which the balloon expands, would conclude that its entire universe was growing, with all neighbors receding. Our situation is similar, except that our universe has 3 spatial dimensions rather than 2, and the expansion is not into some external space we can point to. The expansion is of space itself. Now comes the step that makes this so consequential for the question of origins. If the universe is expanding today, then it was smaller in the past. Run the process backward, like rewinding a film, and the galaxies draw closer together. Go back far enough, and they merge. The space between everything shrinks. The matter that now fills enormous volumes gets compressed into ever smaller regions, and as matter compresses, it heats up. Push the rewind far enough, and you reach a state in which the entire observable universe was packed into a region of extraordinary density and temperature, far hotter than the core of any star, far denser than any material we can create or even imagine. This is the logical consequence of expansion. A universe growing today must have emerged from a much smaller, hotter, denser state in the past. This realization gave birth to what would eventually be called the hot early universe model, the framework within which nearly all modern cosmology operates. The reasoning is straightforward and powerful. We observe expansion now. The laws of physics let us extrapolate backward. That extrapolation leads inevitably to a dense, hot origin. But here is where the trouble begins. and where the seeds of our entire investigation are planted. If you keep rewinding, if you keep compressing the universe into a smaller and smaller volume, the density and temperature do not simply rise to some large but finite value. According to the equations of general relativity, the theory of gravity that governs the large-scale structure of the cosmos, they rise without limit. The universe shrinks toward a single point of infinite density. And at that point, the mathematics that has guided us all the way back simply stops working. This is the singularity, and it deserves careful attention because so much of what follows depends on understanding what it is and what it is not. A singularity in physics is not a thing or a place in the ordinary sense. It is a location in the equations where the quantities being calculated become infinite. Density becomes infinite. The curvature of space-time becomes infinite. Temperature, in principle, becomes infinite. When a well-tested physical theory starts producing infinities, scientists do not usually take those infinities literally. Instead, they take it as a warning sign. It tells them that the theory has been pushed beyond the range where it can be trusted, that some piece of physics has been left out, and that a more complete theory is needed to describe what really happens. We have seen this pattern before in the history of science. When physicists tried to calculate certain properties of hot, glowing objects using the physics of the late 19th century, their equations predicted infinite energy at short wavelengths, an obviously impossible result. That breakdown was not the end of physics. It was the doorway to quantum mechanics, an entirely new framework that resolved the infinity and revolutionized our understanding of nature. The lesson is that infinities in physics often mark the boundary of one theory and the beginning of another, deeper one. The singularity at the start of the universe may be exactly this kind of signpost, pointing toward physics we have not yet fully grasped. And this is the crucial opening through which our whole inquiry proceeds. The standard story says the universe began with a hot, dense state, and that this state traces back to a singularity. But the singularity is not a confident description of a real first moment. It is the point where our current theory of gravity fails. To insist that the universe truly began there, that time itself switched on at that instant, is to take an equation past its breaking point and treat the breakage as a fact. A more cautious view holds that the singularity is a placeholder, a mathematical symptom of our incomplete knowledge, and that something else, something we have not yet described, was happening at and perhaps before that moment. This distinction transforms the question entirely. If the apparent beginning is really just the edge of our understanding, then asking what came before is not necessarily meaningless. It becomes a legitimate scientific question, one that demands a theory capable of describing the extreme conditions where general relativity alone cannot reach. Several such theories now exist, and they fall into a fascinating range. Some propose that the universe emerged from a quantum process that had no earlier time. Others propose that the hot, dense state was not a beginning at all, but a rebound, a bounce from a previous phase of contraction. Still others suggest that what we call the beginning is one link in an endless chain of cosmic cycles stretching infinitely into the past and future. Before we can evaluate any of these possibilities, though, we need to understand the Standard Model far more thoroughly. We need to know not just that it predicts a hot, dense origin, but why it has earned such overwhelming confidence among scientists. A theory does not become the foundation of an entire field by accident. The hot, early universe model make specific, testable predictions, and those predictions have been confirmed with extraordinary precision. To question the beginning responsibly, we must first appreciate the full strength of the evidence that points toward it. Only then can we identify the precise places where that evidence runs out, and the gaps where alternative histories of the cosmos might hide. So the natural next step is to lay out the conventional account in detail, to see exactly what it gets right, and to find the boundaries of what it can actually explain. The strength of the standard cosmological model does not rest on the expansion of galaxies alone. If that were the only piece of evidence, the idea of a hot, dense origin would remain a reasonable extrapolation, but a vulnerable one. What elevated the model from plausible hypothesis to established science was the discovery of independent lines of evidence that all pointed to the same conclusion. When several entirely different observations, made with different instruments and based on different physics, converge on a single picture, scientists gain confidence that the picture is correct. The hot early universe model achieved exactly this kind of convergence, and understanding how it did so reveals both the model's remarkable success and, eventually, the precise points where it leaves questions unanswered. The first and most celebrated piece of corroborating evidence was a faint glow that fills the entire sky. If the universe really did emerge from a hot, dense state, then in its earliest moments, it would have been so hot that matter could not exist in the form of stable atoms. Instead, the cosmos would have been filled with a dense plasma, a churning soup of charged particles, electrons, and atomic nuclei mixed with intense radiation. In such a plasma, light cannot travel freely. Photons, the particles of light, are constantly scattered by the free electrons, bouncing in every direction, unable to move in a straight line for any appreciable distance. The early universe, under this model, would have been opaque, glowing white-hot, but impenetrable, like the dense interior of the sun. As the universe expanded, however, it cooled, and at a certain point, when the temperature dropped low enough, something decisive happened. The electrons slowed enough to be captured by the atomic nuclei, combining to form the first stable, neutral atoms, mostly hydrogen and helium. This event, known as recombination, changed the optical character of the cosmos completely. Once the charged particles bound together into neutral atoms, there were no longer free electrons constantly scattering the light. Suddenly, the photons could travel freely. The universe became transparent. And the light that was streaming through space at that moment of transparency has been traveling ever since, stretched and cooled by billions of years of cosmic expansion, until it reaches us today as a faint background of microwave radiation coming from every direction in the sky. This prediction was made decades before the radiation was found. The logic was clear. If the universe began hot and dense, there should be a relic glow, an afterglow of the primordial fire, red-shifted by expansion into the microwave part of the spectrum and spread uniformly across the heavens. When this cosmic microwave background was finally detected, it represented a stunning confirmation. Here was light that had been traveling almost since the beginning, a direct image of the universe as it was at the moment it became transparent. The temperature of this radiation, measured with great care, matches the prediction of the hot early universe model. Its uniformity across the sky is extraordinary. In whatever direction astronomers point their instruments, the background radiation has very nearly the same temperature, varying by only tiny fractions across vast stretches of sky. That near-perfect uniformity is itself a profound clue, and we will return to it because it conceals one of the deepest puzzles in all of cosmology. But for now, consider what the discovery of this background radiation accomplished. It provided a second, completely independent confirmation of the hot origin. The expansion of galaxies suggested a dense past. The microwave background revealed the actual radiation left over from that dense, hot phase. Two different observations, one based on the motion of galaxies and the other on the relic light of creation, agreed perfectly. The model was no longer a single extrapolation. It was becoming a network of mutually reinforcing evidence. A third confirmation came from the abundance of the lightest chemical elements. According to the hot early universe model, the cosmos in its first few minutes was hot and dense enough to act as a kind of nuclear furnace. In those early moments, before the universe expanded and cooled too much for nuclear reactions to continue, protons and neutrons fused together to build the lightest atomic nuclei. This process, called primordial nucleosynthesis, would have produced specific proportions of hydrogen, helium, and trace amounts of a few other light elements like lithium. The model makes precise predictions about exactly how much of each element should have been created, based on the temperature, density, and rate of expansion in those first minutes. These predictions can be checked against observation. By studying ancient, pristine clouds of gas that have not been significantly altered by the later processing of stars, astronomers can measure the primordial abundances of these light elements. The measurements match the predictions remarkably well. The amount of helium relative to hydrogen, in particular, agrees closely with what the hot early universe model requires. This is a striking achievement. The theory takes the conditions of the universe when it was only minutes old and predicts the chemical composition we observe in the most ancient material, and the prediction holds. Here was a third independent line of evidence, based on nuclear physics rather than on light or motion, pointing once again to the same hot, dense origin. When you assemble these three pillars together, the expansion revealed by galactic redshifts, the relic radiation of the cosmic microwave background, and the abundances of the light elements forged in the first minutes, you begin to understand why the hot early universe model commands such respect. It is not a guess. It is a framework that makes quantitative predictions across wildly different domains of physics, and those predictions are confirmed by independent measurements. A skeptic might explain away any single observation, but explaining away all three, and explaining why they happen to agree with one another, becomes nearly impossible without accepting the underlying model. This is how science builds confidence, not through any single dramatic proof, but through the slow accumulation of independent confirmations that all tell the same story. The model also succeeds in describing the broad sweep of cosmic history that followed. After the universe became transparent, gravity took over as the dominant sculptor of structure. Tiny variations in the density of matter, regions that were very slightly denser than average, began to pull in surrounding material through gravitational attraction. Over millions of years, these slight overdensities grew, accumulating more and more matter until they collapsed into the first stars and galaxies. Those galaxies clustered together into groups and vast filaments, forming the cosmic web of structure we observe today, with galaxies strung along enormous threads surrounding immense, nearly empty voids. The standard model traces this entire developmental sequence, from a nearly smooth hot plasma to the richly structured universe of the present, and it does so with impressive consistency. We can even estimate the age of the universe within this framework. By measuring the current rate of expansion and combining it with our understanding of how that rate has changed over cosmic history, cosmologists calculate how long the expansion has been proceeding. The answer comes out to roughly 14 billion years. This figure is not pulled from thin air. It is cross-checked against other measurements, such as the ages of the oldest stars, which should be younger than the universe that contains them. The fact that the oldest known stars are indeed somewhat younger than the calculated age of the universe provides yet another consistency check, a quiet confirmation that the timeline hangs together. So the Standard Model is genuinely powerful. It is built on solid observational foundations, it makes successful predictions, and it provides a coherent account of how the universe developed from a hot, dense early state into the structured cosmos we inhabit. Anyone who wishes to question whether the universe truly had a beginning must take this success seriously. The model is not a flimsy construction that can be dismissed. It is one of the great intellectual achievements of modern science, and any alternative theory must reproduce all of its successes while also addressing the questions it leaves open. And there are such questions, more than one might expect from a theory so successful. This is the subtle and important point. The Standard Model brilliantly describes what happened from a tiny fraction of a second after the apparent beginning all the way to the present day. But it describes the consequences of an early hot, dense state, without fully explaining the origin or the precise conditions of that state itself. It tells us, in effect, what happened after the curtain rose, but it has remarkably little to say about the curtain itself, about why the universe began in such a specific and peculiar condition, and about what, if anything, preceded it. In particular, the very uniformity of the cosmic microwave background, that nearly identical temperature in every direction, turns out to be deeply puzzling when examined closely. So does the overall geometry of the universe, which appears to be balanced on a knife's edge, in a way that seems to demand explanation. So does the question of where the tiny initial density variations, the seeds of all future structure, actually came from. The Standard Model takes these features as starting conditions, as facts about the early universe that it builds upon. But it does not explain why those starting conditions were what they were. And starting conditions that seem finely tuned, that seem to require very specific values for no apparent reason, make scientists uncomfortable. They suggest that something important is missing from the story. This discomfort is not a weakness to be hidden. It is the engine that drives the field forward. The places where a successful theory falls silent are exactly the places where new physics tends to be discovered. The Standard Model gave us an extraordinary description of cosmic history, and in doing so, it sharpened the questions it could not answer into a precise and pressing form. Those unanswered questions, the puzzles hiding beneath the model's success, are where we must look next, because it is within these very gaps that the possibility of a universe without a beginning first becomes thinkable. The puzzles begin with that uniformity of the background radiation, and to appreciate why it troubles cosmologists so deeply, we have to think carefully about the speed of light and the limits it places on communication across the universe. Nothing, as far as we know, can travel faster than light. This is not merely a rule about how fast objects can move. It is a rule about how fast any influence, any signal, any physical effect can propagate from one place to another. If two regions of space are so far apart that light has not had time to travel between them since the beginning of the universe, then those two regions could never have exchanged anything. No heat could have flowed between them. No information could have passed. They are, in the language of cosmology, causally disconnected. Whatever happens in one can have no effect whatsoever on the other. Now consider the cosmic microwave background again. When we look at one patch of sky and measure the temperature of that relic radiation, then turn to the opposite side of the sky and measure it there, we find the same temperature to extraordinary precision. The two patches match, but here is the difficulty. When that radiation was released, at the moment the universe became transparent, those two opposite patches of sky were already so far apart that light could not have traveled between them in the time available since the beginning. They were causally disconnected. They had never been in contact. There was no way for heat to flow between them, no way for them to come into balance with one another. And yet, they have the same temperature. This is genuinely strange when you sit with it. Imagine you place 2 cups of water in separate rooms, with no connection between them, no shared air, no way for heat to pass from one to the other. You would not expect them to settle at precisely the same temperature by coincidence. If you found that they always did, you would suspect that some hidden connection existed, some shared history that brought them into agreement. The same logic applies to the universe, but on the largest possible scale. Regions of the early cosmos that should never have communicated nonetheless display the same temperature, as if they once shared a common condition. The Standard Model has no explanation for this. It simply takes the uniformity as a given starting condition. But a uniformity that should not exist, given the limits imposed by the speed of light, is not a satisfying starting point. It is a problem demanding a solution. Cosmologists call it the horizon problem, because it concerns regions that lie beyond each other's horizons of possible contact. The second puzzle concerns the overall shape or geometry of the universe. According to general relativity, the presence of matter and energy curves space. The total amount of matter and energy in the universe determines its large-scale geometry. There are 3 broad possibilities. If the density of the cosmos exceeds a particular critical value, space curves back on itself, like the surface of a sphere, and the universe is said to be closed. If the density falls below that critical value, space curves the other way, with a geometry somewhat like a saddle, and the universe is open. And if the density sits exactly at the critical value, space is flat, obeying the familiar rules of ordinary geometry on the largest scales, where parallel lines never meet and the angles of a triangle sum to the expected total. When cosmologists measure the geometry of our universe, they find that it is flat, or so close to flat that any deviation is too small to detect. This might seem unremarkable until you understand how delicate that flatness is. The flat condition is unstable in a particular way. If the early universe had been even slightly denser than the critical value, the curvature would have grown over time, and the universe would have recollapsed long ago. If it had been even slightly less dense, the curvature would have grown in the other direction, and the universe would have expanded so rapidly that matter could never have clumped together into galaxies and stars. For the universe to remain so close to flat after billions of years of expansion, its density in the early moments must have been tuned to the critical value with breathtaking precision, matching it to many decimal places. This is the flatness problem. The Standard Model offers no reason why the early universe should have been balanced so exactly on the dividing line between collapse and runaway expansion. It could have started with any density at all, yet it apparently started with a density fine-tuned to an almost unbelievable degree. When a theory requires its initial conditions to be set with such extraordinary precision, with no underlying reason for that precision, scientists grow suspicious. Such fine-tuning usually signals that a deeper mechanism is at work, something that naturally drives the universe toward flatness, rather than requiring it to begin that way by sheer coincidence. The third puzzle is in some ways the most fundamental of all. The Standard Model describes how tiny variations in density grew under gravity into stars and galaxies and the cosmic web. But it does not explain where those tiny variations came from in the first place. If the early universe had been perfectly smooth, perfectly uniform in density everywhere, then gravity would have had nothing to work with. A perfectly smooth distribution of matter stays smooth, because every region pulls equally on every other, and nothing has any reason to clump. For structure to form, there had to be slight irregularities at the start, regions very slightly denser than average to serve as the seeds around which matter could gather. We observe the imprint of these primordial seeds directly as tiny temperature variations in the cosmic microwave background, the faint ripples superimposed on its overall uniformity. But the Standard Model does not generate these seeds. It assumes them. It takes them as another given starting condition, without explaining their origin or why they have the particular character they do. Notice the pattern in all three of these problems. The horizon problem, the flatness problem, and the question of the seeds of structure are not failures of the Standard Model to describe what happens after the early universe is established. The model handles the subsequent history beautifully. Rather, all three problems concern the initial conditions, the state of the universe at the very beginning of the part we can describe. The model takes that initial state as given and unfolds its consequences with great success. But the initial state itself appears arbitrary, finely tuned, and unexplained. Why was the universe so uniform across regions that could never have communicated? Why was its density balanced so precisely at the critical value? Where did the seeds of structure originate? In each case, the honest answer within the Standard Model is that we do not know. These features are simply assumed. For a scientist, an unexplained coincidence is an invitation. Each of these fine-tuning problems suggests that the early universe underwent some process not captured in the Standard Model, a process that naturally produced uniformity, flatness, and the right kind of density seeds, rather than requiring them to be set by hand at the beginning. If such a process existed, it would mean that the conditions we observe were not arbitrary starting points, but the natural outcomes of physics operating in the earliest moments. The search for that process became one of the central projects of 20th century cosmology, and it eventually produced an idea of remarkable elegance and reach, one that would dominate the field for decades. But before we turn to that idea, it is worth dwelling on a deeper layer of the problem, the one that bears most directly on our central question. All three of these puzzles concern the initial conditions of the universe. But what does it even mean to speak of initial conditions if we cannot describe the beginning itself? Remember the singularity, the point where the equations of general relativity break down and produce infinities. The Standard Model cannot actually describe the first instant. It can only describe the universe from some moment shortly afterward, once conditions had become tame enough for known physics to apply. The true beginning, if there was one, lies hidden behind the singularity, in a regime where our theory of gravity simply fails. This means that the Standard Model's account of the beginning is fundamentally incomplete in a way that goes beyond the fine-tuning puzzles. It is not just that the initial conditions seem arbitrary. It is that the model cannot reach the supposed initial moment at all. It describes a universe that emerged from a hot, dense state, but it cannot tell us how that state came to be, or whether it was truly the beginning of everything, or whether it was instead a transition from something earlier. The singularity is a wall beyond which the Standard Model cannot see, and walls in physics, as we have noted, often turn out to be doorways in disguise. This is the crucial realization that makes alternatives to a singular beginning worth taking seriously. The fine-tuning problems show that the Standard Model's initial conditions require explanation. The singularity shows that the model cannot describe the beginning in any case. Together, these gaps create the intellectual space in which new ideas can take root. If the universe underwent some process before or during its earliest moments that naturally produced the conditions we observe, and if the singularity is not a true beginning, but a breakdown of our equations, masking some deeper physics, then the entire notion of a single, unique origin starts to look less certain. Perhaps the hot, dense state was not the first event, but one event in a longer history. Perhaps the fine-tuning was accomplished not at a beginning, but through a process that could, in principle, have happened more than once. These possibilities remain speculative at this stage. We have only identified the gaps, not filled them. But identifying the gaps precisely is essential, because it tells us what any successful theory of the early universe must accomplish. It must explain the uniformity across causally disconnected regions. It must explain the flatness. It must generate the seeds of structure. And ideally, it should shed light on what lies behind the singularity, on whether the apparent beginning was truly a beginning at all. The first serious attempt to meet at least some of these demands did not directly address the singularity, but it offered such an elegant solution to the horizon, flatness, and structure problems that it transformed cosmology. To understand both its triumph and the new questions it raised, we need to examine it closely, because it sets the stage for everything that follows in our search for a universe that might never have begun. The idea that transformed cosmology proposed that the early universe, for a brief and extraordinary interval, did not expand at the steady pace described by the Standard Model. Instead, it underwent a phase of accelerating expansion, so rapid and so immense that it defies easy comprehension. In a tiny fraction of a second, a fraction so small that ordinary language struggles to convey it, the universe is supposed to have ballooned in size by an enormous factor, stretching by far more than it would expand in all the billions of years that followed. This brief episode of explosive growth came to be called inflation, and it was introduced not as a wild speculation, but as a precise solution to the very fine-tuning problems we have just examined. To understand how inflation solves those problems, begin with the horizon problem, the puzzle of why widely separated regions of the sky share the same temperature despite never having been in contact. Inflation offers an elegant resolution. Before the inflationary burst, the region that would become our entire observable universe was incredibly small, far smaller than in the standard model. In such a tiny region, there was ample time for everything to come into thermal contact, for heat to flow freely, for the whole region to settle into a common temperature. Light could easily cross such a small space, so every part of it could communicate with every other part and reach a uniform condition. Then inflation took hold, and this tiny, thoroughly mixed region was stretched to enormous size in an instant. The uniformity that had been established while the region was small got frozen in and carried along as the region expanded. Regions that appear causally disconnected today, that could not have communicated since the standard beginning, were in fact in close contact before inflation, sharing a common temperature, and inflation merely flung them far apart. The uniformity is not a coincidence. It is the preserved memory of an earlier, intimate connection. The flatness problem dissolves just as neatly. Imagine any curved surface, no matter how strongly curved. Now imagine stretching it by an enormous factor, blowing it up to a vastly larger size. As the surface expands, any local patch of it becomes flatter and flatter, because you are only seeing a tiny portion of a now gigantic curve. The surface of the Earth illustrates this intuition. The Earth is round, but its surface seems flat to us because we occupy such a small portion of such a large sphere. Inflation does the same thing to the geometry of the entire universe. Whatever curvature the universe possessed before inflation, the colossal expansion stretched it out so dramatically that the observable region was driven extraordinarily close to flat, regardless of how it started. The flatness we observe is not a finely tuned initial condition. It is the inevitable consequence of enormous expansion. Inflation flattens the universe, the way inflating a balloon flattens any wrinkle on its surface. And the third problem, the origin of the density seeds that grew into galaxies, finds perhaps the most beautiful resolution of all within the inflationary picture. To understand it, we need to bring in the quantum nature of the world. At the smallest scales, the universe is not smooth and continuous, but restless and uncertain. The principles of quantum mechanics tell us that even empty space is never perfectly still. It seethes with tiny fluctuations, momentary variations in energy that appear and disappear constantly. A kind of irreducible jitter built into the fabric of reality at the most fundamental level. Ordinarily, these quantum fluctuations are far too small to matter on any scale we can observe. They operate in the realm of the subatomic, invisible to our largest telescopes. But inflation changes this dramatically. During the inflationary burst, the same enormous expansion that flattened the universe and smoothed out its temperature also seized upon these tiny quantum fluctuations and stretched them to macroscopic, even cosmic scales. A fluctuation that began as an imperceptible quantum ripple in a microscopic region was inflated, along with everything else, into a variation spanning vast distances. In this way, inflation took the inherent quantum jitter of the early universe and magnified it into slight variations in density across the cosmos. These stretched-out fluctuations became the seeds of structure, the regions very slightly denser than average that would later, under the patient pull of gravity, grow into stars, galaxies, and the great cosmic web. The pattern of these primordial density variations, according to inflation, should have a particular statistical character, a specific distribution across different scales. And remarkably, when cosmologists examined the tiny temperature variations in the cosmic microwave background, the faint ripples in that relic radiation, they found a pattern strikingly consistent with the inflationary prediction. This is what made inflation so compelling. A single idea, a brief episode of accelerated expansion in the first instant of cosmic history, simultaneously solved three independent problems that had troubled the Standard Model. It explained the uniformity of the background radiation, the flatness of space, and the origin of the seeds of structure, all at once, with one mechanism, and it made a testable prediction about the statistical pattern of those seeds, a prediction that observation appeared to confirm. For an idea to resolve several distinct puzzles with a single stroke, and then to pass an observational test it could have failed, is exactly the kind of success that earns a theory widespread acceptance. Inflation rapidly became the dominant framework for understanding the very early universe, an extension of the Standard Model that pushed our description back to within a tiny fraction of a second of the apparent beginning. What drove this inflationary expansion? The proposed mechanism involves a special kind of energy, a form of energy associated with a field that filled the early universe. The details are technical, but the essential idea can be grasped. Under certain conditions, this field could possess a peculiar property. It could carry energy in a form that, through the equations of general relativity, produces a kind of repulsive gravitational effect. We are accustomed to thinking of gravity as always attractive, always pulling things together. But general relativity allows for the possibility that certain forms of energy can drive space to expand rather than contract, pushing outward instead of pulling inward. The energy of the inflationary field is supposed to have done exactly this, driving the rapid accelerating expansion that defines inflation. Then, after its brief reign, the field released its stored energy. The inflationary expansion ended, and that released energy transformed into the hot, dense bath of particles and radiation that constitutes the starting point of the standard hot early universe model. In this picture, inflation does not replace the Standard Model. It precedes it and sets it up, providing the explanation for why the Standard Model's initial conditions were what they were. This handoff is an important conceptual point. The Standard Model begins with a hot, dense state and asks us to accept its uniformity, flatness, and density seeds as given. Inflation reaches back to an earlier moment and explains how that hot, dense state acquired those very properties. The end of inflation produces the beginning of the standard story. The two frameworks fit together, with inflation supplying the prologue that the Standard Model had been missing. For many cosmologists, this represented a profound advance. It meant that the seemingly arbitrary fine-tuning of the early universe was not arbitrary at all, but the natural product of a physical process, and that process left observable fingerprints in the relic radiation that we could measure and check. For a time, it seemed that inflation might even address the deepest question of all, the question of the beginning itself. Some versions of the theory suggested intriguing possibilities about how inflation might start and stop in different regions, leading to pictures in which inflation, once begun somewhere, might continue forever in some sense, spawning region after region. These ideas hinted at a cosmos far larger and stranger than the observable universe, and they raised the possibility that our universe might be one part of something vastly more extensive. We will explore the implications of such pictures later, because they bear directly on the question of whether the cosmos as a whole had a beginning even if our particular region did. But for now, the crucial point is that inflation, for all its success, did not actually resolve the problem of the singularity. It pushed our understanding back to an extraordinarily early moment, to within a sliver of a second of the apparent origin. It explained the conditions of the hot, dense state. Yet inflation still requires a starting point. The inflationary field had to begin in a particular condition for inflation to occur. And the question of how that condition arose, of what came before inflation, of whether inflation itself emerged from a singularity, remained open. Inflation moved the boundary of our ignorance, but it did not remove it. Behind the inflationary epoch, the same fundamental question still loomed. Was there a true beginning, a first moment, or did inflation itself emerge from some prior state? There is a deeper concern as well, one that has occupied cosmologists for years. A series of theoretical analyses suggested that inflation, despite its successes, cannot by itself avoid the need for a beginning. The reasoning, developed carefully over time, indicated that any universe that has been expanding on average throughout its history, as inflation requires, cannot be extended infinitely far into the past. Such a universe must have a boundary in time, a point beyond which the inflationary description cannot continue. In other words, inflation does not describe an eternal past. It still seems to require some kind of starting point, some initial condition from which the whole process began. If this reasoning holds, then inflation, for all its power to explain the conditions of the early universe, does not free us from the question of origins. It still points back toward a beginning, even if it cannot describe that beginning itself. This is a subtle but vital realization. Inflation solved the fine-tuning problems brilliantly, and it remains a cornerstone of modern cosmology, supported by observation. But it did not answer whether the universe began. It explained why the early universe looked the way it did, while leaving the ultimate question of origins as mysterious as ever, and perhaps even sharpening it. If inflation requires a beginning, and if that beginning is hidden behind a singularity our theories cannot penetrate, then we have made enormous progress in understanding the early universe, while making no progress at all on the deepest question. And this tension, this sense that the leading theory illuminates so much, yet leaves the central mystery untouched, is precisely what motivates the search for a different kind of cosmology, one in which the beginning might not be a beginning at all. Before we can pursue that search, though, we must look more closely at the difficulties within inflation itself, at the ways in which even this triumphant theory raises questions it cannot answer. For all its explanatory power, inflation rests on foundations that are less secure than its widespread acceptance might suggest. And examining these weaknesses is essential, because they help explain why some cosmologists have looked beyond inflation altogether toward fundamentally different accounts of the early universe. The first difficulty concerns the very mechanism that drives inflation. The theory requires a special field with a special form of energy, the field whose repulsive gravitational effect powers the rapid expansion. But what is this field? In the most basic versions of the theory, it is not a field that has been independently observed, or that arises naturally from established physics. It was introduced specifically to make inflation work. This does not make it wrong, but it does make it provisional. A mechanism invented to solve a problem, and not yet connected to the rest of known physics, carries a certain fragility. Cosmologists have proposed many different versions of the inflationary field, with many different properties, and the observations do not clearly select one version over the others. The theory, in other words, is flexible, perhaps too flexible. This flexibility leads directly to a deeper concern. A scientific theory gains strength from making sharp predictions, predictions that could fail and thereby prove the theory wrong. The most powerful theories are those that stick their necks out, that say the world must be one specific way and not another. Inflation, in its general form, is so adaptable that critics have questioned whether it makes sharp enough predictions to be tested decisively, because there are so many possible versions of the inflationary field, with so many adjustable properties. The theory can accommodate a wide range of observations. If one version is ruled out by measurement, another can often be constructed to fit. This adaptability is a double-edged quality. It allows inflation to match the data, but it also raises the worry that the theory can match almost any data, and a theory that can explain anything risks explaining nothing in particular. This concern has been raised by serious physicists, including some who helped develop inflationary ideas in the first place, and it remains a live debate within the field. A further problem concerns the initial conditions required for inflation to begin. Inflation was introduced, in large part, to explain why the universe did not require finely tuned initial conditions. The whole appeal of the theory was that it took an arbitrary, unexplained starting state and showed how natural physical processes could produce the uniformity and flatness we observe. But careful analysis suggests that inflation itself may require special conditions to get started. For the inflationary field to begin in the state needed to drive the rapid expansion, certain conditions must already be in place across a region of space. If those conditions are themselves improbable or finely tuned, then inflation has not fully solved the fine-tuning problem. It has merely relocated it, pushing the need for special initial conditions back to an earlier stage. The universe must already be somewhat smooth and somewhat ordered for inflation to begin smoothing and ordering it. This circularity troubles some cosmologists. A theory meant to eliminate fine-tuning should not secretly depend on fine-tuning of its own. Then there is the problem that arises from inflation's own internal logic, sometimes the most unsettling difficulty of all. In many versions of the theory, once inflation begins, it does not stop everywhere at once. Quantum fluctuations, the same fluctuations that seed the structure of the universe, also affect the inflationary field itself. In some regions, these fluctuations cause inflation to end, producing a hot, dense universe like our own. But in other regions, the fluctuations keep the inflationary field aloft, and inflation continues. Those still inflating regions expand far faster than the regions where inflation has ended, so they quickly come to dominate the total volume. Within them, new regions stop inflating, becoming new universes, while still other regions keep inflating, and the process continues without end. This is the picture of eternal inflation, in which inflation, once started, never completely stops, perpetually spawning new regions, new pockets, new universes, in an endless cascade. Eternal inflation has profound and disorienting consequences. If it is correct, then our observable universe is just one pocket among an unimaginably vast, perhaps infinite, collection of such pockets, each potentially with different properties. This is one route to the idea of a multiverse, a cosmos so large and so varied that it contains countless distinct regions, each a universe in its own right. Some find this picture exhilarating. Others find it deeply problematic. because it threatens the predictive power of the theory. If inflation produces an infinite variety of universes with an infinite variety of properties, then almost anything we might observe could be accommodated somewhere in the vast ensemble. The theory loses its grip on specific predictions. When everything that can happen does happen somewhere, the notion of predicting what we should observe becomes mathematically and philosophically treacherous. Cosmologists have struggled for years with how to extract definite predictions from a theory that generates infinite possibilities, and the problem remains unresolved. But the difficulty most relevant to our central question is the one we touched on at the close of the previous discussion. Inflation does not avoid the need for a beginning. The careful theoretical analyses indicating that any universe expanding on average throughout its history must have a past boundary applied to inflation as well. An eternally inflating universe expands on average as you trace it forward. But trace it backward, and the reasoning suggests it cannot continue infinitely into the past. There must be some boundary, some initial condition from which the whole inflationary process emerged. Eternal inflation may be eternal toward the future, endlessly spawning new universes, but it does not appear to be eternal toward the past. And so, the question of the beginning returns undiminished. Inflation explains a great deal about the universe we observe, but it does not tell us whether time itself had a first moment. If anything, it sharpens the question, because it shows that even an apparently endless inflationary process still seems to require a starting point. This is the crux of the matter. Inflation is a remarkable theory, supported by real evidence, capable of explaining the uniformity and flatness of the cosmos and the origin of its structure. Yet it does not resolve the deepest puzzle. It leaves the singularity untouched. It may require fine-tuning of its own. It raises troubling questions about predictability through eternal inflation, and it still seems to demand a beginning it cannot describe. For cosmologists drawn to the possibility that the universe might have no beginning at all, these difficulties are not reasons to abandon inflation entirely, but they are reasons to wonder whether inflation is the whole story, or whether some different framework might do better at the deepest level. It is worth being fair to inflation here. None of these difficulties prove it false. Many cosmologists regard inflation as well established and view its problems as puzzles to be solved within the inflationary framework rather than reasons to discard it. The observational successes are real. The pattern of fluctuations in the cosmic microwave background matches inflationary predictions with impressive accuracy, and no rival theory has clearly surpassed it on the full range of evidence. Science does not abandon a successful theory merely because it has open questions. Every theory has open questions. The proper response is to keep testing, to keep refining, and to keep alternatives in mind in case new evidence shifts the balance. Inflation remains the leading account of the early universe, and any challenger must match its successes before it can claim to replace it. And yet the open questions are real too, and they point in a particular direction. The problem of the beginning, the problem of the singularity, the problem of what came before. These are not minor technical wrinkles. They concern the very foundation of cosmic history. A theory that explains everything after the first instant, while leaving the first instant itself in shadow, has accomplished something extraordinary. But it has not finished the job. The shadow over the beginning is exactly where the most radical possibilities live. If inflation requires a beginning it cannot describe, then perhaps the right move is to question the assumption that there was a beginning at all. Perhaps the hot, dense state, and even the inflationary epoch that may have preceded it, was not the start of everything, but a phase in a longer story. A story that extends back before the moment we have been treating as the origin. This is the conceptual turning point in our investigation. Up to now, we have followed the standard model and its inflationary extension, theories that assume, even if they cannot describe, a beginning. We have seen their successes and their limits. Now we begin to consider a different family of ideas, ideas in which the universe does not begin at a singularity, but instead emerges from a previous state, ideas in which the cosmos may cycle, bounce, or flow endlessly from one phase to the next. These ideas are old in their intuition and new in their mathematical form. They take seriously the possibility that the singularity is not a wall, but a doorway, that what looks like a beginning is actually a transition, and that time may extend infinitely far into the past, with no first moment at all. To approach these ideas properly, we should first recognize that the intuition behind them is ancient. Long before modern cosmology, human cultures imagined a universe that repeats, that dies and is reborn, that moves in great cycles without beginning or end. These were not scientific theories, but they expressed a deep human sense that perhaps existence has no single starting point, that perhaps the natural rhythm of the cosmos is not birth from nothing, but eternal recurrence. Modern physics has, in a sense, returned to this ancient intuition, but armed now with equations, observations, and the hard discipline of testable prediction. The marriage of that old intuition with the rigor of modern science has produced some of the most intriguing cosmological proposals of our time. To understand them, we begin with the idea of eternal return, and how a notion once confined to myth and philosophy found a new and unexpected home in the mathematics of the universe. The intuition that the cosmos moves in cycles, that it has no single beginning, but instead repeats through endless rounds of creation and dissolution, appears again and again across human history, long before anyone could express it in the language of physics. Many ancient traditions conceived of time not as a straight line running from a first moment to a final one, but as a great wheel turning through vast ages, each ending in dissolution and giving rise to the next. The specifics varied enormously from one culture to another, and these were frameworks of myth and contemplation rather than science. But the underlying picture, a universe without ultimate beginning or end, recurring through immense cycles, recurs so often in human thought that it seems to answer something deep in the way we intuit time and existence. The notion that everything that exists must have started at some definite moment is not the only way the human mind has approached the question. The alternative, that existence simply is, eternally, cycling without origin, has an equally long pedigree. When modern cosmology emerged in the 20th century and revealed that the universe is expanding, it might seem that the cyclic intuition was decisively defeated. An expanding universe traced backward leads to a hot, dense origin, apparently a beginning. But almost immediately, thoughtful scientists noticed that expansion alone does not settle the matter. The crucial question is whether the expansion continues forever or eventually reverses. And this depends on the contents of the universe and the geometry of space, on whether gravity is strong enough to halt the expansion and pull everything back together. If the universe contains enough matter, then gravity, acting across cosmic distances, might gradually slow the expansion, bring it to a stop, and then reverse it, initiating a phase of contraction. The galaxies, having flown apart, would begin to fall back together. Space, having stretched, would begin to shrink. And if that contraction continued, the universe would head toward a hot, dense state once again. A mirror image of the hot, dense state from which it apparently emerged. This realization opened a door that expansion alone had seemed to close. If the universe could expand and then contract, then perhaps the contraction need not end in a final, permanent collapse. Perhaps it could lead to another expansion, a new cycle, and if one cycle could follow another, then perhaps cycles had been occurring all along, stretching back infinitely into the past. The expanding universe we observe would then be just the current phase of an endlessly repeating process, the latest in an unbounded series of expansions and contractions. The hot, dense state we call the beginning would not be a beginning at all, but a transition between one cycle and the next, the moment when a previous contraction gave way to our present expansion. In this picture, the singularity is reinterpreted. It is not the origin of everything, but the hinge between cycles, the point of maximum compression where one phase ends and another begins. This is the essential idea of the oscillating universe, and its appeal is considerable. It offers a way to sidestep the problem of the beginning entirely. If the universe has always been cycling, then there is no first moment to explain, no singular origin to account for. The question of what came before the beginning dissolves, because there was no beginning. There was only the previous cycle, and before that another, and before that another, without end. The cyclic picture replaces the troubling notion of a unique origin with the more symmetric notion of eternal recurrence, in which the cosmos is simply doing what it has always done, expanding and contracting through endless ages. For those who find the idea of an absolute beginning philosophically or scientifically unsatisfying, this offers a profound alternative. But intuition and appeal are not enough in science. A cyclic universe must work in detail. It must be consistent with the equations of physics and with what we observe. And when scientists first examined the oscillating universe carefully, using general relativity, they encountered serious difficulties. Difficulties that would eventually lead most of them to set the idea aside for decades. The first and most immediate problem was the singularity itself. For the universe to bounce from contraction back into expansion, it must pass through, or somehow avoid, the state of maximum compression. But general relativity predicts that a contracting universe heads toward a singularity, a point of infinite density where the equations break down completely. Just as the equations cannot describe the supposed beginning, they cannot describe the supposed bounce. At the moment of maximum compression, the theory fails. There is no smooth, well-defined way, within general relativity alone, for a contracting universe to turn around and begin expanding again. The bounce, the very heart of the cyclic idea, lies in the region where our theory of gravity cannot reach. This was a genuine obstacle. Without a mechanism for the bounce, the oscillating universe was less a theory than a hope. One could imagine cycles, but one could not show how the transition between them actually worked. The singularity stood in the way, just as it stood in the way of describing the beginning. In a sense, the cyclic picture traded one singularity problem for many. Instead of a single unexplained origin, It now had an unexplained transition at the end of every cycle. Unless physics could describe what happens at the moment of maximum compression, the cyclic universe could not be a complete theory. It pointed toward the same gap in our knowledge that haunted the Standard Model, the gap where general relativity gives way to something deeper, presumably a theory that unites gravity with the quantum nature of matter and energy. But the singularity was not the only problem. There was a second difficulty, arising from one of the most fundamental laws of physics, a difficulty that seemed for a long time to doom the cyclic universe regardless of how the bounce might work. This is the problem of disorder, of the relentless tendency of physical systems to become more disordered over time, a tendency captured by the concept of entropy. We will examine entropy in much greater depth later, because it sits at the very center of the debate over cyclic cosmology. But the essential point can be stated now. In any physical process, the total disorder of a closed system tends to increase. Ordered, low disorder states evolve into disordered, high disorder states, and the reverse essentially never happens spontaneously on large scales. A cup of hot coffee cools to room temperature, mixing its concentrated heat into the surroundings. The reverse, room temperature coffee, spontaneously heating itself by drawing energy from its cooler surroundings, never occurs. This one-way increase of disorder defines an arrow of time, a direction in which physical processes naturally proceed. Now apply this to a cyclic universe. If disorder always increases, then each cycle should be more disordered than the last. The universe would carry the accumulated disorder of all previous cycles forward into each new one. Over many cycles, the disorder would pile up relentlessly, and this leads to observable consequences that early analyses found troubling. As disorder accumulated, each successive cycle would be expected to behave differently from the one before, in ways that did not match a universe that simply repeats. The build-up of disorder seemed to prevent the universe from truly resetting itself, from starting each cycle fresh. Instead of an eternal, unchanging recurrence, the cyclic universe would be a degrading process, each cycle a worn copy of the last, with no way to return to a pristine starting condition. Trace this backward, and the accumulation of disorder seemed to imply that there could not have been infinitely many past cycles, because infinitely many cycles would have produced infinite disorder. The cyclic picture, meant to avoid a beginning, seemed forced back toward one after all by the inexorable increase of entropy. Between the singularity problem and the entropy problem, the oscillating universe fell out of favor. It remained an intriguing idea, a tantalizing possibility, but it did not seem to work as a rigorous physical theory. The bounce could not be described, and the accumulation of disorder seemed to forbid eternal cycling. For a long stretch of the 20th century, most cosmologists focused on the Standard Model and its inflationary extension, setting the cyclic idea aside as an elegant notion that the mathematics would not support. The ancient intuition of eternal return seemed, once again, to have been defeated, this time not by the discovery of expansion, but by the deeper laws of gravity and thermodynamics. And yet, the idea never entirely died, because the problems it faced were not necessarily fatal. They were challenges, and challenges in physics are sometimes overcome by new ideas. The singularity problem reflected the limits of general relativity, but general relativity is known to be incomplete. It does not incorporate quantum mechanics, and at the extreme densities near a singularity, quantum effects on gravity should become important. A future theory of quantum gravity might describe what general relativity cannot, might show how a bounce could occur smoothly without an actual singularity. The entropy problem was more subtle, but it too rested on assumptions that could be questioned. What if the universe did not simply contract and re-expand at the same size each time, but grew larger with each cycle, diluting the accumulated disorder? What if the geometry of space, or the role of some new form of energy, allowed disorder to be spread out so thinly that each cycle could begin effectively fresh? These were speculative possibilities, but they suggested that the cyclic idea might be revived if the right physics could be found. The revival, when it came, did not simply resurrect the old oscillating universe. It transformed the cyclic idea using new theoretical tools that had not been available to earlier generations of cosmologists, tools drawn from attempts to unify the forces of nature and to describe gravity in quantum terms. These new frameworks offered fresh ways to think about the bounce, about extra dimensions of space, and about how disorder might be managed across cycles. The result was a new generation of cyclic models, more sophisticated and more carefully constructed than their predecessors. Models that took the ancient intuition of eternal return and rebuilt it on the foundation of modern theoretical physics. To understand these models, we must first look more closely at the obstacles they had to overcome, beginning with the question that defeated the original oscillating universe, the question of what actually happens when a universe stops expanding and begins to contract, and whether such a contraction must inevitably end in collapse, or might instead lead somewhere new. What would it actually mean for the universe to stop expanding and begin to contract? To take the cyclic idea seriously, we have to think carefully about this reversal, because it is the pivot on which the entire picture turns. Today, every observation tells us the universe is expanding, and not merely expanding, but expanding at an accelerating rate, a fact we will examine in depth later because it complicates the cyclic picture enormously. But set that complication aside for the moment and imagine, as the early cyclic theorists did, a universe in which gravity eventually wins. Imagine that the expansion slows, halts, and reverses. What would such a contracting universe be like, and where would it lead? In the earliest moments of a reversal, almost nothing would seem to change. The universe is so vast, and the reversal so gradual, that on human timescales, and even on the timescales of stars and galaxies, the transition from expansion to contraction would be imperceptible. Galaxies that had been drifting apart would slowly cease their mutual recession and begin, ever so gradually, to approach one another. But this would unfold over spans of time so immense that any individual observer, any civilization, any star, would experience only an infinitesimal slice of the process. The contraction would begin in silence, a turning so slow that it would take an enormous stretch of cosmic time before its effects became noticeable on the largest scales. As contraction continued over billions of years, however, the consequences would mount. The space between galaxies, having stretched for so long, would begin to shrink. Galaxies that had receded to enormous distances would slowly draw closer. The light from distant galaxies, which in our expanding universe is shifted toward the red end of the spectrum, would instead begin to shift toward the blue, as the contracting space compressed the light waves rather than stretching them. An observer in such a universe, measuring the light of distant galaxies, would find a universal blue shift rather than a red shift. the unmistakable signature of a cosmos falling inward rather than flying apart. This blue shift would be the mirror image of the red shift that first revealed cosmic expansion to us, and it would mark the universe's transition into its contracting phase. As the contraction accelerated, driven by the relentless inward pull of gravity, the universe would grow progressively denser and hotter. This is the reverse of what happened during expansion. Just as expansion cooled the universe, allowing matter to condense and structure to form, contraction would heat it, undoing that structure step by step. The process would proceed in stages, each undoing one of the achievements of cosmic history. First, the large-scale structure of the cosmos would be compressed. The vast voids between the filaments of galaxies would shrink. Clusters of galaxies drawn together would begin to merge. The careful architecture of the cosmic web, built up over billions of years of gravitational assembly, would be steadily dismantled as everything was forced closer together. Eventually, as the contraction continued, the density of matter and radiation would rise to the point where the background radiation that fills the universe, currently a cold whisper of microwaves, would be compressed and heated until it became significant once more. In the present universe, this relic radiation is so cold and faint that it has no appreciable effect on the temperature of space. But in a contracting universe, that radiation would be squeezed into ever smaller volumes, raising its temperature steadily. There would come a time when the sky itself, currently dark between the stars, would begin to glow, first faintly, then more brightly, as the compressed background radiation heated toward the temperatures that prevailed in the early universe. The darkness of space, which we take for granted, is itself a consequence of expansion, and contraction would slowly undo it. As temperatures climbed, the conditions necessary for life and for the existence of complex structures would vanish. Stars would find themselves bathed in an increasingly hot background, until the space around them became hotter than their own surfaces, disrupting the delicate balance that allows a star to shine. Planets would be rendered uninhabitable long before the final stages. The universe would become, once again, a hot and increasingly uniform environment, the structures of billions of years dissolving back into the smooth, hot state from which they emerged. The arrow of cosmic development, which had pointed from simplicity toward complexity, from a hot, smooth plasma toward galaxies and stars and worlds, would reverse, pointing now from complexity back toward simplicity, from structure back toward smoothness. Continuing inward, the contraction would reach conditions resembling the early universe in reverse. The temperature would rise to the point where atoms could no longer hold together, where the electrons would be stripped from their nuclei, and the universe would return to a state of hot plasma, opaque once more to light, just as it had been before the moment of transparency in the distant past. The neutral atoms that formed during recombination would be torn apart, and the cosmos would revert to the churning, glowing soup of charged particles that characterized its early hot phase. Further compression would push conditions back toward those of primordial nuclear synthesis, where even atomic nuclei could not survive intact, where the building blocks of matter would be broken down into their constituents under the rising heat and density. And then, as the contraction approached its extreme, the universe would head toward the state of maximum compression, the mirror image of the hot, dense state from which it apparently began. The density would climb toward enormous values, the temperature would soar, all the matter and energy of the cosmos would be crushed into an ever smaller volume. This is the state that early cosmologists called the Big Crunch, the contracting counterpart of the hot, dense beginning. It represents the end point of contraction, the moment when everything that the universe contains is compressed toward a single, extraordinarily dense and hot condition. In the original oscillating models, this crunch was supposed to be the turnaround point, the moment when contraction would somehow give way to a new expansion, the hinge between one cycle and the next. But here we encounter, once again, the problem that defeated the early cyclic models. As the universe approaches the crunch, the density and temperature rise toward infinity, and general relativity predicts a singularity, just as it does for the beginning. The equations break down. There is no smooth, well-defined way within general relativity alone for the contraction to reverse into expansion. The crunch in the classical picture is not a turnaround, but an endpoint, a place where the theory simply stops being able to describe what happens. The universe heads toward infinite density, and the mathematics gives no account of any subsequent expansion. The bounce that the cyclic universe requires lies precisely in the region where our best theory of gravity fails. This is why the question of the crunch is so closely tied to the question of the beginning. They are, in a sense, the same problem viewed from opposite directions. The beginning is a singularity in the past, the place where contraction, if there was any, would have given way to our expansion. The crunch is a singularity in the future, the place where our expansion, if it ever reverses, would give way to contraction's end point. In both cases, the issue is the same. General relativity predicts a singularity, a breakdown of the equations at the moment of maximum compression. And in both cases, the resolution, if there is one, must come from physics beyond general relativity, from a theory that can describe what happens at densities and temperatures so extreme that the classical description of gravity no longer applies. There is a further question that the contracting universe forces us to confront, one that connects directly to the entropy problem we touched on earlier. A contracting universe is not simply an expanding universe run backward in every respect. The arrow of time, the direction in which disorder increases, does not obviously reverse just because the universe begins to contract. Even as the cosmos shrinks, the disorder built up over its entire history, the disorder of all the stars that have burned, all the structures that have formed and dissolved, all the irreversible processes that have occurred, would persist and continue to grow. The contracting universe would not be a clean reversal of the expanding one. It would carry the accumulated disorder of its entire past into the crunch, and this raises the central difficulty for any cyclic model. If each cycle carries forward the disorder of the previous one, then the cycles cannot be identical. They cannot truly repeat. The crunch would not deliver a fresh, pristine universe ready to begin anew, but a universe burdened with the accumulated disorder of everything that came before. This is the knot that any serious cyclic theory must untie. It must explain how the universe can pass through the crunch, through the region where general relativity fails, and emerge into a new expansion. And it must explain how the new cycle can begin in a state ordered enough to develop structure again, rather than being suffocated by the disorder inherited from the previous cycle. These two challenges, the bounce and the entropy, are the great obstacles that brought down the original oscillating universe. To revive the cyclic idea, modern theorists had to find ways to address both. The first step is to understand how a contraction might lead not to a final, singular collapse, but to a smooth turnaround, a bounce that carries the universe from contraction back into expansion without passing through a true singularity. This is where the new physics enters, the physics that the early cyclic theorists did not have, and it is to the mechanism of the bounce that we now turn. How could a universe collapsing toward infinite density possibly avoid that fate and rebound into a new expansion? This is the central technical question of cyclic cosmology, and answering it requires going beyond general relativity, because general relativity by itself offers no escape. The theory predicts a singularity, and at a singularity it ceases to function. To describe a bounce, physicists must appeal to physics that takes over precisely where general relativity fails, in the regime of extreme density and tiny scales, where the quantum nature of reality can no longer be ignored. The bounce, in other words, is fundamentally a problem of quantum gravity, the long-sought theory that would unite Einstein's account of gravity with the quantum mechanics that governs the behavior of matter and energy at the smallest scales. We do not yet possess a complete and confirmed theory of quantum gravity. This is one of the great unfinished tasks of physics, perhaps the greatest. But we have several promising candidate frameworks, partial theories, that attempt to describe how gravity might behave in the quantum realm. And these frameworks offer tantalizing hints about how a bounce might occur. The key insight that many of them share is that the classical singularity, the point of infinite density, predicted by general relativity, may not actually be reached. Instead, when the density becomes extreme enough, new physical effects may emerge that resist further compression, that push back against the inward collapse, halting it before infinity is reached and turning it around into expansion. If this is correct, then the singularity is not a real feature of the universe, but an artifact of using an incomplete theory, and the true behavior near maximum compression is a smooth bounce rather than a catastrophic breakdown. Consider one way this might work, drawn from approaches that apply quantum principles to the geometry of space itself. In these frameworks, space is not infinitely divisible. It cannot be compressed without limit. At the smallest scales, the very fabric of space may have a discrete, granular character, a fundamental smallest size, below which the notion of distance loses its ordinary meaning. If space cannot be compressed beyond this fundamental scale, then a contracting universe cannot collapse all the way to a point of infinite density. As it approaches the fundamental scale, the quantum nature of space asserts itself, and a powerful, effective repulsion arises, a resistance to further compression built into the geometry of space at the deepest level. This repulsion would halt the contraction and reverse it, producing a bounce. The universe would shrink to a minimum size, a tiny but finite scale set by the fundamental granularity of space, and then rebound into expansion, beginning a new cycle. In this picture, the singularity is replaced by a bounce, and the moment that classical physics describes as infinite density becomes instead a moment of extreme but finite density, a turning point rather than an end point. This is a profound conceptual shift. In the classical picture, the contraction leads to a singularity, a place where everything ends and the equations give no further guidance. In the quantum bounce picture, the contraction leads to a moment of maximum, finite density, after which expansion resumes. The universe passes smoothly through the moment of greatest compression and emerges on the other side, expanding once more. There is no infinite density, no breakdown of physics, no true singularity. There is only a bounce, a turnaround, a hinge between one cycle and the next. If such a mechanism is correct, then the great obstacle to cyclic cosmology, the singularity problem that defeated the original oscillating models, may be overcome. The bounce becomes describable, at least in principle, by physics that goes beyond general relativity into the quantum regime. Different theoretical frameworks propose different specific mechanisms for the bounce, but they share this common theme. Whether through the granular nature of space, through new forms of energy that become repulsive at extreme densities, or through other quantum gravitational effects, the goal is the same: to show how a contraction can avoid the singularity and reverse into expansion. Some models invoke special forms of matter or energy with unusual properties that, under extreme compression, exert a kind of negative pressure that drives the universe to expand rather than collapse. Others rely on the detailed structure of higher dimensional theories, which we will explore shortly. The diversity of approaches reflects the fact that we do not yet know which, if any, is correct. But the existence of multiple plausible mechanisms suggests that a bounce is not obviously impossible, that the singularity may indeed be an artifact of an incomplete theory rather than an unavoidable feature of reality. It is worth pausing to appreciate how much this reframing changes the conversation about the beginning. If a bounce is possible, then the hot, dense state we observe in our past need not have been a beginning. It could have been the bounce itself, the moment when a previous contracting universe reversed and became our expanding one. The apparent origin would then be a transition, the latest in a possibly endless series of bounces. The question of what came before the beginning would have an answer: the previous cycle, with its own stars and structures and history, collapsing toward the bounce that gave rise to our universe. Time would extend back through that previous cycle and the cycle before it without any first moment. The bounce mechanism, if it works, removes the absolute beginning and replaces it with eternal recurrence, with cycles stretching back infinitely into the past. But a working bounce mechanism, while necessary, is not sufficient to make a cyclic universe viable. Recall the second great obstacle, the problem of entropy, the accumulation of disorder across cycles. Even if we can describe how the universe bounces from contraction to expansion, we still face the question of whether the new cycle can begin in a sufficiently ordered state to develop structure, or whether it is doomed to inherit the disorder of all previous cycles. A bounce that simply carries forward the accumulated disorder would produce a degrading sequence of cycles, not the clean, repeating recurrence that the cyclic idea envisions. The bounce solves the singularity problem, but it does not by itself solve the entropy problem. A complete cyclic cosmology must address both. This is where the modern cyclic models become genuinely ingenious, because they propose ways to handle the entropy problem that the early oscillating models never considered. One key idea involves the size of the universe at the bounce and the role of expansion in diluting disorder. Suppose that the universe does not simply contract back to the same size from which it expanded, but rather that each cycle involves a vast amount of expansion, far more than is needed to return to the starting size. During the long expansion phase, the universe grows enormously, and the disorder it has accumulated becomes spread out across an immense volume, diluted to an extraordinarily low density. Then, if the contraction and bounce involve only a portion of this expanded universe, or if the relevant disorder is diluted away during the expansion, each new cycle could begin with the disorder spread so thinly that it has effectively been reset. The accumulated disorder is not destroyed, but it is diluted into irrelevance by the sheer scale of the expansion, allowing each new cycle to begin effectively fresh. This dilution mechanism is subtle and depends on the details of how the universe expands and contracts, but it offers a possible escape from the entropy problem that doomed the original oscillating models. Instead of each cycle inheriting the concentrated disorder of the previous one, the disorder is spread out across an ever-expanding volume, so that the density of disorder, the disorder per unit volume, returns to a low value at the start of each cycle. The total disorder may increase from cycle to cycle in accordance with the fundamental law, but the disorder that matters for the development of structure, the disorder in any given region, can be reset by expansion. This reconciles the cyclic universe with the relentless increase of total disorder, while still allowing each cycle to begin in an ordered enough state to develop galaxies and stars. Whether this resolution truly works remains a matter of active debate among cosmologists, and we will return to the entropy problem in greater detail later, because it is the single most serious challenge to cyclic cosmology and deserves careful scrutiny. But the existence of plausible mechanisms for both the bounce and the dilution of disorder represents enormous progress beyond the original oscillating models. The early cyclic universe failed because it could describe neither the bounce nor the management of entropy. The modern cyclic models propose solutions to both, drawing on quantum gravity for the bounce and on the dynamics of expansion for the dilution of disorder. They are not confirmed theories, but they are serious, mathematically developed proposals that take the ancient intuition of eternal recurrence and rebuild it on a foundation of contemporary physics. There is something deeply appealing about this reconstruction. It suggests that the problems which once seemed to doom the cyclic universe were not fundamental impossibilities, but reflections of the limits of older theories. General relativity could not describe the bounce, but quantum gravity might. The simple oscillating model could not manage entropy, but a model with sufficient expansion might. As our theories deepen, possibilities that once seemed closed reopen. The cyclic universe, abandoned for decades, returned not as a revival of the old idea, but as a new family of theories, more sophisticated and more carefully constructed, addressing the very problems that had defeated their predecessors. And among these new approaches, one stands out for its boldness and its grounding in attempts to unify the fundamental forces of nature, an approach that locates the bounce not in our familiar three dimensions of space, but in a hidden architecture of extra dimensions, where vast membranes drift through a higher dimensional realm, and their collisions ignite new cosmic cycles. To understand this remarkable proposal, we must first venture into the strange and counterintuitive world of higher dimensions. The idea that space might have more than three dimensions sounds, at first, like pure fantasy, the kind of notion that belongs in speculative fiction rather than serious physics. We perceive three dimensions of space, length, width, and height, and our intuition rebels at the suggestion that there could be more. Yet the possibility of extra dimensions has become a respectable and even central feature of some of the most ambitious attempts to unify the laws of physics. To understand how extra dimensions enter cosmology, and how they give rise to one of the most striking cyclic models, we need to understand why physicists were led to consider them in the first place, and how dimensions beyond our familiar three could exist without our ever noticing them directly. The motivation comes from the long quest to unify the forces of nature. Physics recognizes several fundamental forces, including gravity, electromagnetism, and the forces that operate within atomic nuclei. These forces appear, at first glance, to be entirely distinct, governed by different rules and operating on different scales. But physicists have long suspected that this apparent diversity conceals an underlying unity, that the different forces are aspects of a single deeper structure, much as electricity and magnetism, once thought separate, were eventually understood as two faces of a single electromagnetic force. The dream of unification, of showing that all the forces of nature emerge from one fundamental framework, has driven theoretical physics for generations. And in pursuing this dream, physicists discovered something unexpected. The mathematics of unification seemed to work more naturally, more elegantly, if space had more than 3 dimensions. The leading framework in which this occurs proposes that the fundamental constituents of reality are not point-like particles, but tiny vibrating entities, often described as strings, whose different modes of vibration correspond to the different particles and forces we observe. This framework, in its various forms, requires for its mathematical consistency that space have more dimensions than the 3 we perceive. The exact number depends on the specific version of the theory, but the essential point is that the equations only work, the theory only holds together, if there are additional spatial dimensions beyond the familiar 3. This was not a feature anyone set out to include. It emerged from the mathematics, an apparently unavoidable consequence of trying to build a consistent theory that unifies gravity with the other forces at the quantum level. The theory seemed to be telling physicists that the universe has more dimensions than we directly experience. But if there are extra dimensions, why do we not perceive them? Where are they? The traditional answer is that the extra dimensions are compactified, curled up so small that we cannot detect them directly. Imagine a long, thin garden hose viewed from a great distance. From far away, the hose looks like a one-dimensional line, having only length. But up close, you can see that it has a second dimension, a circular dimension wrapping around its circumference. A small insect crawling on the hose could move along its length or around its circumference, experiencing both dimensions. But from a distance, that circular dimension is invisible, too small to notice, and the hose appears one-dimensional. The idea is that our universe's extra dimensions might be like the circular dimension of the hose, curled up at every point in space into sizes so small that they escape direct detection, while the 3 large dimensions we perceive are like the length of the hose, extended and obvious. This compactification picture dominated thinking about extra dimensions for a long time. But it is not the only possibility, and an alternative possibility gave rise to the cyclic model we are building toward. What if not all the extra dimensions are curled up small? What if there is a large extra dimension, an additional dimension of space, extended like our familiar 3, but inaccessible to us for a different reason? This is the idea that leads to the concept of brains, and it requires a genuine stretch of the imagination. But the payoff is a remarkable picture of how cosmic cycles might work. The term brain comes from membrane, and the idea is this: Suppose that our entire observable universe, all three of our familiar spatial dimensions, and everything they contain, all the galaxies, stars, planets, and the radiation that fills space, is confined to a kind of membrane, a three-dimensional sheet embedded within a higher dimensional space. The matter and forces we know, including light and the particles that make up everything we see, are stuck to this membrane, unable to leave it, confined to its three dimensions. We can move freely within the membrane throughout our three dimensions of space, but we cannot move off it into the higher dimensional space in which it is embedded. From our perspective, the membrane is the entire universe, because we cannot perceive or access anything beyond it. The extra dimension extends perpendicular to our membrane, into a realm we cannot enter, but it is there nonetheless, a large extra dimension in which our membrane floats. This is a strange picture, and it deserves a careful analogy to make it tangible. Imagine beings who live on the two-dimensional surface of a vast sheet of paper. They can move left and right, forward and back, throughout their two-dimensional world. But they have no awareness of the third dimension, the direction perpendicular to the paper, up and away from the surface. They cannot move in that direction, cannot perceive it, cannot even conceive of it easily. Their entire universe is the surface of the paper. Now suppose there is another sheet of paper, parallel to theirs, floating a small distance away in that third dimension they cannot perceive. The beings on the first sheet would have no direct knowledge of the second sheet. They could not see it or touch it, because everything they can interact with is confined to their own surface. The second sheet would exist in a direction entirely inaccessible to them. This is the relationship that brain cosmology proposes between our universe and other possible brains. Our universe is one membrane, and there may be others, parallel to ours, floating at a small distance in an extra dimension we cannot perceive or enter. The reason gravity might behave differently in this picture is subtle and important. In many brain scenarios, while ordinary matter and light are confined to the membrane, gravity is not. Gravity, in these theories, can extend into the extra dimension, reaching across the gap between brains. This distinction between gravity, which can leave the membrane, and everything else which cannot, plays a crucial role. It means that two parallel brains, though unable to exchange matter or light, could still interact gravitationally across the extra dimension. They could feel each other's presence through gravity, could be attracted to one another, could move toward each other through the higher dimensional space. And this gravitational interaction between brains opens the door to a remarkable mechanism for cosmic cycles, one in which the collision of two brains plays the role of the bounce, the hot, dense event that we experience as the beginning of a cosmic cycle. Before we explore that collision in detail, it is worth dwelling on how radically this picture reframes our notion of the universe. In the standard view, our universe is everything, all of space and time, with nothing outside it because there is no outside. In the brain picture, our universe is a single membrane within a larger, higher dimensional space, and there may be other membranes, other universes, alongside ours, separated from us by a dimension we cannot traverse. The hot, dense beginning we observe would not be the beginning of all existence, but an event within this larger structure, an event involving the dynamics of brains in higher dimensional space. The realm beyond our membrane, the extra dimension, and whatever else floats within it, would constitute a vastly larger reality, of which our universe is only a part. This is a humbling and expansive vision. It suggests that the limits of our perception, the three dimensions we experience, may not be the limits of reality. Just as the beings on the sheet of paper could not perceive the third dimension in which their world was embedded, we may be unable to perceive the higher dimensions in which our universe is embedded. And just as those beings might be utterly unaware of a parallel sheet floating nearby, we may be unaware of parallel universes, other brains, existing alongside ours in the extra dimension. The mathematics that led physicists to extra dimensions did so in pursuit of unifying the forces of nature, but the consequences reach far beyond that original goal, opening up a picture of reality far richer and stranger than the universe of three dimensions we thought we inhabited. Of course, all of this remains theoretical. We have no direct evidence that extra dimensions exist, no observation that confirms the existence of brains or higher dimensional space. The theories that predict them are mathematically sophisticated and elegant, but elegance is not proof. The extra dimensions, if they exist, have so far eluded all attempts at direct detection, which is why they must be either curled up small or otherwise inaccessible to our instruments. The brain picture is a hypothesis, a possibility suggested by our best attempts to unify physics, not an established fact. But it is a possibility taken seriously by serious physicists, and it leads to a specific and testable scenario for cosmic cycles. If our universe is a membrane in higher dimensional space, and if there is another membrane parallel to ours, then the two could collide. And that collision, the meeting of two universes across the extra dimension, might be exactly the event we have been searching for. The bounce that begins a cosmic cycle. The hot, dense state that we mistake for the beginning of everything. To understand how two brains could collide and what such a collision would produce, we now turn to the dynamics of these higher dimensional membranes and the cataclysmic yet cyclical events their meetings could ignite. Picture two vast membranes, each a three-dimensional universe in its own right, floating parallel to one another across a thin gap in a higher dimension. They cannot see each other, cannot exchange light or matter, for everything except gravity is confined to each membrane separately. But through gravity, reaching across the extra dimension, they sense one another's presence. And under the right conditions, this gravitational interaction draws them together. Slowly, across spans of time that dwarf the entire history of our observable universe, the two brains approach. The gap between them narrows. And eventually, they meet, colliding across the full extent of their three-dimensional expanse, every point of one membrane striking the corresponding point of the other at nearly the same moment. This collision, according to the cyclic brain model, is the event we experience as the hot, dense beginning of our universe. It is the bounce, reinterpreted as the meeting of two worlds. The physics of this collision is what makes the model so compelling as a solution to the bounce problem. When the two brains collide, the enormous energy of their impact is converted into the matter and radiation that fill the universe. The kinetic energy of the approaching brains, the energy of their motion through the extra dimension, is transformed at the moment of collision into a hot, dense bath of particles and radiation spread across the entire three-dimensional extent of the membrane. This is precisely the hot, dense state that the standard model takes as its starting point, the state from which expansion, cooling, and the formation of structure proceed. But in the brain model, this state is not a singularity, not a point of infinite density. It is the result of a collision, an event with finite energy spread across the vast expanse of the membranes. The infinite density of the classical singularity is avoided because the hot, dense state arises from the collision of extended membranes rather than from the compression of everything to a single point. This is the crucial advantage of the brain collision picture. The bounce, the transition from one cycle to the next, occurs through a physical process that does not require passing through a true singularity. The brains approach, collide, release their energy into matter and radiation, and then recede from one another, beginning a new cycle. The collision is hot and dense, but it is not infinitely so. The geometry of our three large dimensions does not collapse to a point. Instead, the extra dimension, the gap between the brains, momentarily shrinks to zero at the moment of collision, and then reopens as the brains separate. From our perspective, confined to the membrane, we experience only the consequences within our three dimensions. The sudden appearance of a hot, dense state, filling all of space, followed by expansion. We cannot perceive the extra dimension or the approach and recession of the brains. We see only the aftermath of the collision, which looks to us like a hot beginning. Let us trace the full cycle as the brain model describes it, because the elegance of the picture lies in how naturally it produces an endless sequence of cosmic ages. Begin at the moment of collision. The two brains meet, and their impact fills our membrane with hot, dense matter and radiation. This is what we would call the hot beginning. The brains then begin to separate, moving apart in the extra dimension. As they separate, our membrane, our universe, expands and cools, just as the standard model describes. Matter condenses, structure forms, galaxies and stars assemble, and the universe develops into the richly structured cosmos we observe. Over enormous stretches of time, the universe continues to expand, the galaxies drift apart, and the cosmos grows ever larger and emptier. This long phase of expansion corresponds to the entire history of our universe as we know it, from the hot beginning to the present and far beyond. But the brains, having separated, do not simply drift apart forever. The gravitational attraction between them, reaching across the extra dimension, eventually slows their separation, halts it, and draws them back together. This turnaround in the extra dimension occurs while our three-dimensional universe continues to expand. Here is a subtle and important point. The approach of the brains in the extra dimension does not correspond to a contraction of our three large dimensions. Our universe can continue to expand even as the brains move back toward each other. The dynamics in the extra dimension and the dynamics within our membrane are, to a degree, independent. So while we experience continued expansion of our three-dimensional space, the brains are silently approaching one another through the dimension we cannot perceive, and eventually they collide again, releasing another burst of hot, dense matter and radiation, beginning the next cycle. The collision resets the contents of the universe, filling it once more with the hot, dense state from which a new round of cosmic evolution proceeds. This cyclic brain scenario has several attractive features that distinguish it from the original oscillating universe. First, as we have emphasized, it provides a mechanism for the bounce that avoids the singularity. The hot, dense state arises from a collision, not from the compression of everything to a point of infinite density. Second, it offers a natural way to address the entropy problem, the accumulation of disorder across cycles. Because our three-dimensional universe expands enormously during each cycle, the disorder produced in one cycle is diluted across an ever-growing volume. By the time the next collision occurs, the disorder from the previous cycle has been spread so thin across such an immense expanded space that it is effectively negligible in any given region. Each new cycle begins, in effect, with a clean slate, not because the disorder has been destroyed, but because the vast expansion has diluted it into irrelevance. The collision then fills the universe with fresh, hot, dense matter, and a new cycle of structure formation begins. This handling of entropy is one of the most ingenious aspects of the model. Recall that the original oscillating universe failed in part because disorder accumulated from cycle to cycle, preventing the cosmos from truly resetting. The brain model addresses this by ensuring that each cycle involves a tremendous amount of expansion, so much that the disorder of the previous cycle is diluted away before the next collision. The total disorder of the entire structure may increase over the cycles, in accordance with the fundamental law that disorder tends to increase. But the disorder that matters for the evolution of our membrane, the disorder per unit volume within our three dimensions, is reset by the expansion. This allows the cyclic process to continue indefinitely, with each cycle resembling the others, without the degradation that doomed the original oscillating models. We will scrutinize this claim more carefully when we examine the entropy problem in depth, because not all cosmologists are persuaded that it fully succeeds. But as a proposed solution, it represents a genuine advance. A third attractive feature of the brain model is that it may reproduce the observational successes of inflation without requiring inflation itself. Recall that inflation explains the uniformity of the cosmic microwave background, the flatness of space, and the origin of the density seeds that grew into structure. The cyclic brain model attempts to explain these same features through different means. The uniformity and flatness arise because the brains, before collision, are smooth and flat across their vast extent, having been stretched and flattened during the long expansion phase of the previous cycle. The collision, occurring nearly simultaneously across the entire membrane, produces a hot, dense state that is correspondingly uniform. And the density seeds, the tiny variations that grow into galaxies, arise from quantum fluctuations in the brains as they approach, fluctuations that produce slight variations in the timing of the collision from place to place, which translate into slight variations in density in the resulting hot state. In this way, the brain model aims to account for the same observations that inflation explains, but through the dynamics of colliding brains, rather than through a burst of accelerated expansion. Whether the brain model actually succeeds in matching all the observational details as well as inflation does is a matter of ongoing investigation and debate. The pattern of density seeds in particular must match the precise statistical character observed in the cosmic microwave background, and reproducing this pattern in the brain model requires careful work. Some analyses suggest the brain model can match the observations. Others identify difficulties. The model is not a finished, confirmed theory, but a serious proposal under active development, competing with inflation as an account of the early universe. What makes it especially interesting for our central question is that, unlike inflation, it does not require a beginning. The cycles extend infinitely into the past, each collision preceded by a previous expansion, each expansion preceded by a previous collision, without any first moment. The brain model offers a genuine alternative to the picture of a singular origin, a universe that has been cycling forever, with no beginning to explain. There is something philosophically satisfying about this picture, and also something that strains the imagination. On one hand, it removes the need for a beginning, replacing the mysterious singular origin with an endless sequence of brain collisions. On the other hand, it requires us to accept the existence of extra dimensions, of brains, of a higher dimensional reality in which our universe is merely one membrane among possibly many. It trades one mystery, the beginning, for another, the existence of an unseen higher dimensional structure. Whether this trade is worthwhile depends on whether the brain model can be tested, whether it makes predictions that distinguish it from inflation and from a singular beginning. And this question of testability is crucial, because a theory that cannot be tested, however elegant, remains speculation rather than science. The brain model is not the only modern approach to a universe without a beginning. There is another, quite different proposal, one that does not rely on extra dimensions or colliding brains, but instead on a radical reinterpretation of how one universe might connect to the next. This alternative envisions not a collision, but a seamless flow, in which the distant future of one universe becomes, in a precise mathematical sense, the beginning of the next. It is a strange and beautiful idea, grounded in deep features of the geometry of space-time, and it offers yet another way to imagine a cosmos with no first moment. To understand it, we must consider what happens to a universe in its extreme old age, when all the stars have died and only the faintest radiation remains, and how that desolate far future might, against all intuition, become the seed of a new beginning. Imagine the universe in its extreme old age, an unimaginably distant future, far beyond the death of the last star. To grasp this alternative cyclic proposal, we have to follow our own universe forward, not backward, to its ultimate fate, because this approach locates the transition to the next cycle, not at a hot, dense collision, but at the cold, empty end of cosmic history. This requires us to think about what the universe becomes after all the processes we know have run their course, after the galaxies have exhausted their ability to form new stars, after the existing stars have burned out, after even the most exotic remnants have faded. It is a portrait of cosmic death, and yet in this proposal, it is precisely this death that gives rise to new life. Follow our universe forward in time. Right now, the universe is full of stars, shining across the galaxies, forging heavy elements in their cores and scattering them into space when they die. But star formation cannot continue forever. The raw material for new stars, the clouds of gas that collapse to ignite fresh stellar fires, is finite. As that material is used up, fewer and fewer new stars form. Over immense stretches of time, the existing stars age and die. The most massive stars burn brightly and die quickly, collapsing into dense remnants or exploding and leaving behind exotic cores. The smaller stars, which burn their fuel slowly, last far longer, but even they eventually exhaust their fuel and fade. There comes a time, almost inconceivably far in the future, when the last star flickers out and the universe goes dark, no longer illuminated by the light of stellar fusion. The era of starlight, which seems to us so fundamental a feature of the cosmos, is only a passing phase, destined to end. But the death of the stars is not the end of cosmic evolution. The dead remnants of stars, along with the dark matter that pervades the universe, continue to drift through space, bound by gravity into the remains of galaxies. Over still longer stretches of time, these remnants interact gravitationally, and many of them are drawn toward the centers of galaxies, where enormous concentrations of mass have gathered. The universe in this era is a place of cold, dark objects, the burnt-out cores of former stars, drifting through an ever-expanding space, occasionally interacting, but mostly isolated in the growing emptiness. And at the centers of galaxies lurk the most extreme objects in the cosmos, regions where matter has collapsed so completely that not even light can escape their gravitational grip. These objects grow over time, swallowing the matter that falls into them, becoming ever more massive as the eons pass. Yet even these most extreme and seemingly permanent objects are not eternal. According to deep principles connecting gravity, quantum mechanics, and thermodynamics, even these regions of total gravitational collapse slowly lose energy over time, radiating it away through a subtle quantum process at their boundaries. This radiation is extraordinarily faint, almost imperceptibly slow, but over timescales so vast that they make the current age of the universe seem like an instant, it causes these objects to gradually shrink. They lose mass, slowly at first, then faster as they grow smaller, until finally, after spans of time almost beyond comprehension, they evaporate entirely, releasing their last energy in a final burst and vanishing from the cosmos. With their disappearance, the last great concentrations of mass in the universe are gone. What remains is an exceedingly thin, cold sea of radiation and the lightest, most stable particles spread across an enormous and still expanding space. This is the ultimate fate of the universe under our current understanding, a state often described as the far future of cosmic history. The universe becomes nearly empty, containing only the faintest radiation and a sparse scattering of stable particles, spread across an immense volume that continues to expand. The temperature approaches the lowest possible values. There is essentially no structure, no concentration of matter, nothing but a thin, cold, nearly uniform bath of radiation extending in all directions, growing ever more dilute as the expansion proceeds. This is a portrait of maximal disorder, of a universe that has run down completely, that has reached a state from which no further interesting change seems possible. It is, in the conventional view, the end of the story, a cold, dark, empty eternity stretching forward without end. But the proposal we are now considering takes this desolate far future and finds in it the seed of a new beginning through a remarkable insight about the geometry of such a universe. The key observation is this: in the extreme far future, when the universe contains only radiation and no massive particles, something peculiar happens to the very notion of scale and size. To understand this, we need to appreciate the difference between objects that have mass and objects that do not. Massive particles, like the protons and electrons that make up ordinary matter, provide a kind of natural ruler, a standard of size, because their mass defines a definite scale. But radiation, the massless particles of light, has no such intrinsic scale. Light does not carry a built-in standard of size in the way that massive particles do. And in the far future, when all the massive particles have decayed or been swept away, when the universe contains essentially only radiation, the universe may lose its sense of scale entirely. This is a subtle and profound point. If the universe in its far future contains only massless radiation, then there is nothing to define what counts as large or small, because the only objects present, the particles of light, do not carry an intrinsic scale. Under these conditions, the proposal suggests, the enormous, cold, dilute far future of the universe becomes, in a precise mathematical sense, indistinguishable from a hot, dense early state. The two states, the cold, empty far future and the hot, dense beginning, which seem like complete opposites, become geometrically equivalent when there is no scale to distinguish them. The vast, cold, empty end of one universe can be mathematically identified with the tiny, hot, dense beginning of the next. The far future flows seamlessly into a new beginning, not through a collision or a bounce, but through this loss of scale that makes the end and the beginning geometrically the same. This is the central idea of the conformal cyclic proposal, and it requires careful explanation because it is so counterintuitive. The word conformal refers to a kind of transformation that preserves angles and the structure of light paths, but ignores absolute scale, that treats large and small as equivalent. The proposal holds that in the far future, when only radiation remains, the universe's physics becomes governed by relationships that do not care about absolute scale, that are conformal in this technical sense. And under such physics, the immense cold expanse of the far future can be smoothly rescaled, mathematically, into the compact hot state of a new beginning. The end of one cosmic age, properly understood, is the beginning of the next. There is no collision, no compression, no bounce in the ordinary sense. There is a seamless geometric transition in which the desolate far future of one universe becomes the fiery birth of the next. In this picture, the entire history of our universe, from its hot beginning to its cold, empty far future, is a single cosmic age, one link in an endless chain of such ages. The proposal calls each of these ages an aeon, and the cosmos consists of an infinite sequence of aeons, each beginning in a hot, dense state and ending in a cold, empty expanse that flows into the hot beginning of the next. Our universe, our entire cosmic history, is just one ion among infinitely many, preceded by countless aeons before it, and followed by countless aeons after. There is no first aeon and no last. The chain extends infinitely in both directions, with no beginning and no end. The hot state we observe in our past is the transition from the previous aeon, the far future of a universe that ran its course before ours began. This proposal handles the entropy problem in its own distinctive way, quite different from the brain model. Recall that disorder tends to increase, and that this seems to forbid the universe from resetting. The conformal cyclic proposal addresses this through the role of the extreme objects at the centers of galaxies and their eventual evaporation. The idea is that these objects, the regions of total gravitational collapse, effectively destroy information and disorder as they form and grow, and that their eventual complete evaporation removes this disorder from the universe. By the time the far future arrives, the disorder that had accumulated has, in this view, been processed and removed through the formation and evaporation of these extreme objects, allowing the far future to reach a state of low effective disorder that can serve as the beginning of a new aeon. This is a controversial claim, touching on deep and unresolved questions about the nature of information and disorder in the presence of total gravitational collapse, and it is one of the most debated aspects of the proposal. But it represents an attempt to solve the entropy problem through the physics of cosmic death, rather than through the dilution of expansion. The conformal cyclic proposal is bold, beautiful, and highly speculative. It rests on assumptions that are not yet established, particularly the assumption that all massive particles eventually decay, leaving only radiation, and the assumption about how disorder is removed through the evaporation of the extreme objects. Not all physicists accept these assumptions, and the proposal remains at the frontier of speculative cosmology. But it offers a genuinely different vision of a universe without a beginning, one in which the cycles are not driven by collisions or bounces, but by the deep geometry of space-time and the loss of scale in the far future. And remarkably like the brain model, it makes a claim that can potentially be tested, a claim that a previous aeon might leave faint imprints on our own, observable traces of the universe that existed before ours. This possibility that we might actually detect evidence of a previous cosmic age transforms these speculations from pure theory into potential science, and it raises the tantalizing question of what, if anything, could survive the transition from one cycle to the next, carrying information across the boundary between universes.